Welcome to this third part of this tutorial. My name is Thomas Kesselheim. I'm from Bonn, and I will be talking about profit inequalities via balanced prices. These balanced prices, these are a very particular but very powerful approach towards giving you profit inequalities. So it's designing profit inequalities, which we've actually seen in both the first and the second part. But to keep things self-contained, I'll just repeat almost everything that you'll need to know in order to understand what I'm talking about. So the problem that I'd like to have in mind here is the following. Namely, this is the following combinatorial auction problem, which we've seen before. Namely, we have these n buyers arriving one by one, and we have m items. At each arrival, we have to decide which of the items to assign to the current buyer, maybe none, and our goal is to maximize social welfare. And these allocations are immediate and irrevocable. So for example, this guy might show up, he would have a value of 1 for the first item, a value of 2 for the second item, a value of 2 for both items together. Let's not give him anything. This lady now has a value of 0 for the first item, a value of 2 for the second, sorry, a value of 10 for the second item, and a value of 10 for both items together. Let's give her the second item. Now this guy has a value of 5 for either the first or the second item, or also for both items together. But the second item is already gone, so we might give him, for example, the first item. Now this lady shows up, she would have a value of 80 for both items together, but unfortunately we're out of items, so we cannot give her anything, which means that our social welfare now would be 15 as opposed to 80, which we could have achieved by, for example, giving her both items. In this part of this tutorial, I'd now like to first consider the case of a single item in this setting, which is exactly the standard profit inequality. And then I want to talk about this setting for where I have multiple items, and I'll then introduce the notion of balanced prices there. And then I'll extend this further to even other feasibility structures, for which we then also generalize the notion of balanced prices. But let's first talk about this single item. So the single item case would now be the classic profit inequality. We have n buyers arriving one by one, and we have one item. And the goal, of course, simplifies now to stopping the sequence at the highest number. So we would have somebody who has a value of 15 for the item. He does not get the item. She has a value of 10 for the item. Let's keep the item. He now has a value of 30 for the item. You might get it. And she might have a value of 80 for the item. Okay, we cannot give her the item because the item has already been allocated. Good. So the question is now, how does our performance of our way of allocating the item compare to the best optimum in hindsight, so the maximum of all the values that we have in this sequence? And the profit inequality setting, once again summarized here, is the following. We have these n buyers of values v1 through vn. We have one item, and now these buyers arrive online one after the other. Each of them reveals their vi, and then we immediately and irrevocably have to decide whether to assign the item or to keep it. And we are now assuming that these values are drawn independently from known probability distributions. And these buyers arrive in a fixed order. So you could, in principle, relax this to not knowing in advance in which order the buyers will arrive. But to keep things simple, let's just assume that they actually arrive in order 1 through n. And then the standard profit inequality tells us that there exists an algorithm for which the expected social welfare that you're achieving is at least a half times the expected value of the optimal solution, which in this case is a half times the expectation of the maximum in that sequence. And although you've seen the proof of this in both parts before, I'd like to once again go through the arguments of how you would do this. Because then we'll see how to generalize actually this argument, or what also turns out to be the core of this argument. So what would you do? You have this one item and you have these n buyers. Each has some value which you don't know beforehand, but you know which distribution it is drawn from. And what you now do is the following. You would define any price for this item. Let's call this P. And this defines a probability that the item is sold. For every price that we define, we get a probability that the item is sold. Namely, what's the probability that one of the values is at least the price? And now, how much money would we collect? What would be the expected revenue? It would be nothing but the price times the probability that the item is sold. And what is a buyer's utility? So what's their value minus the payment? In expectation, it's the following. It's the positive part of their value minus the price, but only if nobody before them bought the item. And then you can use independence and bound this probability that nobody before I bought the item by the probability that the item is not bought at all, so that you can say, okay, the expected utility is at least the expectation of the positive part of buyer I's value minus the price times 1 minus Q, where Q was the probability that the item is sold. And now you can just combine these two bounds. Namely, the expected welfare is nothing but the expected revenue plus the sum of the expected utilities. And we can plug this in, and then we just do some basic calculus. Namely, we bound this sum of these non-negative random variables by the maximum. We drop this plus here so that this might also be negative. And this is where we end up, which is some PQ plus the expectation of the maximum minus P times 1 minus Q. And this holds for every price that we could define. And now the magic happens that, for example, we can set the price to 1/2 times the maximum value in that sequence. And what now happens is that, okay, this probability Q, which we don't know, this doesn't actually matter anymore. Because regardless of what Q is, this expression here will always be exactly 1/2 times the expectation of the maximum. And somehow, when we're now trying to generalize this, this is exactly the idea that we're following. Because let me try to even simplify the argument, or let me try to come to the essence of what is happening here. Because things get even easier, things get even more obvious if I consider the case that these values, that I know these values in advance. And then, of course, I could stop the sequence here at the highest number. But what I'm actually doing in this other argument is I'm setting a price to something like 1/2 times the maximum in that sequence. And I don't claim that this is a good price. I claim that this is a balanced price. What does this make a good price? What does this make a balanced price? Well, let's consider this lady here. She has the highest value. Let I be the one having the highest value. Now, what can happen? Well, only one of two cases will occur. Either somebody before this lady bought the item. Well, then the revenue is high. The revenue is at least 1/2 times her value. So everything's fine. Or nobody before her bought the item. Well, then she can buy the item, and the utility is at least her value minus the price she has to pay. So in this case, it's just 1/2 times her value. And the point is that this argument you can extend to the incomplete information world by, well, roughly speaking, writing expectations around everything. And this is exactly the idea of balanced prices, that you kind of do some, you're able to do such a full information argument, which is robust enough so that you can actually write expectations around everything, and this way get an argument also for this incomplete information setting where you only know the probability distributions. So in either case, I forgot to mention here the welfare, which is the revenue plus the sum of the utilities is at least half of the optimum value. Good. Now let's turn to this combinatorial auction setting. In this combinatorial auction setting, what I now like to do is I want to even devise a very simple algorithm as a very simple mechanism. Namely, I want to post prices to the items. So I have these n bars arriving one by one. Each of them has a valuation function, which is drawn from a probability distribution. This probability distribution is known to me in advance. And then I want to pre-compute some item prices based on the knowledge of these distributions, such that whenever a buyer arrives, they may just purchase their utility maximizing bundle, and this gives me a good approximation of the optimal social welfare. So in this case, I might not have a price of 4 for the first item, a price of 5 for the second item. And now this guy here, he wouldn't buy anything because he would have negative utility if he bought item 1 or item 2 or both items together. So he will not buy anything. But she has a utility of 5, for example, for buying the second item. She would have a utility of 1 for both items together, but would maximize her utility is actually buying only item 2. Now he has a utility of 1 when buying the first item, so he will do this. He cannot buy the second item because the second item is already gone. So of course, this utility maximizing bundle, this is only taking over all remaining items at this point. Now, what will be important to solve or to get any approximation guarantees is what can you assume regarding these valuation functions? And what we'll now first assume is that these are XOS or fractionally subadditive functions. What are XOS functions? They are defined like this, but I'll have a few examples in a second. So a function is XOS if it is a pointwise maximum over additive functions, which means the following. You would have here values like Vij superscript L, where this is now for a fixed L, this would be just some additive function. So you would just add up these Vij's for a fixed L for the items that you're getting, and then you're taking the maximum over all possible L. What might this look like? Well, there's the very simple case of an additive function. Then you don't need this maximum, and then you can just set Vij to the value that you have for item J, and then you're good. Your value of a set is just the sum of the values of the items inside that set. Or what you can also capture is a unit demand function, which is that your value for a set is just the value of the item you value most in that set. How would you capture this? You would have now, for a fixed L, all of these Vij would be 0 except for one of them. And so what you actually only make use of is this maximum and not so much that sum, because, well, there's only one item which contributes to this value. Now, if you look at these unit demand functions, you will realize, okay, under such a setting, it makes no sense to assign more than one item to a buyer because, well, all that counts is the most valuable of the items. And actually, this combinatorial auction setting is nothing but the bipartite matching setting that Michal was talking about, where you have vertex arrivals. So the vertices, this would be the buyers here. And so this combinatorial auction setting that we're talking about here, this actually generalizes these this bipartite matching setting. And you can actually have much more interesting functions, like, for example, budget additive function. Well, this is not so super interesting, but this is also a typical XOS function. So your value for a set of items is somewhat additive. It's adding up the values for the items in that set, but it is capped at a certain budget B. Or more generally, every submodular function is XOS. So whenever you have these decreasing marginals, whenever adding an item to a set gives you a a larger, or well, it can only give you a larger increase when you add it to a set S than if you add it to a superset of the set S. So these are typical examples of XOS functions. This is a very powerful and easy to work with class of valuation functions. And for these XOS functions, there's this fantastic result by Feldman, Graven, and Lucier, which is the following. If we have any distributions over XOS functions, there exist static anonymous item prices such that the following is true. The allocation that we're achieving by now, each buyer just purchasing their preferred bundle of items based on these prices that we're computing, the expected social welfare of this allocation fulfills that it is at least half times the expected optimal social welfare. A very simple special case of this is that we have only one item, and then this is nothing but the standard profit inequality, because all we have is that we have n buyers who have each a certain value for the item, and we then just post one item price, and we see who is the first buyer to buy this item. And this result actually shows us that this 1/2, which turned out to be optimal even for the standard profit inequality, works out in a much more general sense, namely even for these XOS combinatorial auctions. And how does this work? Well, the key technique to do this is using balanced prices. I've already given you an idea of what balanced prices are about, but let's go a little more into details of what I mean by balanced prices. Namely, I'll call a valuation function good if it admits prices which are not too low and not too high. And these are the definitions that I have for not too low and not too high. Let's see this maybe in a couple of examples. My first example is just some really boring additive function. My value for a set of items is just the number of items that I'm getting. And let's now assume that I'm targeting these 3 items. So actually, I should be getting these 3 items in the set U. This is what I call the set U, which will make sense later. So this is the set of items that I'm supposed to get. Now I claim setting a price of 1 for every item is good. Why that? Well, on the one hand, these prices are not too high because I can now afford to buy every subset of the items. For every subset of the items, the sum of the prices is no larger than my value for these items. For example, I could buy all 3 items, then I would have to pay 3, but my value would also be 3. And in fact, I have this here fulfilled with equality for every possible set. Now, on the other hand, these prices are not too low. What do I mean by this? Well, if now somebody else came along and bought a set of items T, they would have to pay the sum of the prices inside that set T. And what I now want is that the prices that they have to pay is at least the value that they are taking away from me. So what's that? This is the value that I had for all items beforehand, and now I'm left with only the set U take away T. And so the difference of these two, this is how much value they're taking away from me. And for example, if they take away this set of items 2 and 3, then my remaining value will be 1, but they are paying 2, which makes up for exactly the value that I'm losing, because my value before was 3. Now I have a value of only 1 remaining. Now things get a little more interesting if I turn to this unit demand function, where my value for a set of items is 1 if it is non-empty, and for the empty set, I have a value of 0. So whenever I get at least 1 item, my value is 1. Even if I get multiple items, it will still be 1. Now here I claim these prices would be good prices. They are not unique here, but these would be good prices. I claim that these prices, setting price of 1 for item 1 and price of 2 for price of 0 for item 2, price of 0 for item 3, this would be good prices. Why aren't they too high? Well, every set of items I can pay for because the sum of the prices for these items never exceeds my value. Here, in fact, it might, for example, be that I'm buying only item 2, then I would have to pay nothing, but my value would be 1. So this might be also an inequality here. But at the same time, I claim that these prices are not too low. And you should now, again, keep the same thing in mind. There's now somebody taking away a set of T of items away from me. And how much are they paying versus how much value are they taking away from me? Well, they might, for example, take away these 2 items from me. Then they have to pay nothing. Okay, so I have 0 here on the left-hand side, but on the right-hand side, I have how much value am I losing? Well, I'm not actually losing any value because my value for the first item alone is still 1. So the difference here would also be 0. If they buy all 3 items, then suddenly my remaining value will be 0, but then I'm also covered by how much they are paying for this item. And this now you can also do in a more general way. For example, if you have a budget additive function, then you can also define prices like this, which fulfill both these inequalities. In my example here, I would now have a value of number of items, but at most 1.5. Well, then I could, for example, set prices like this, having a price of 0.5 for the first item, price of 1 for the second item, a price of 0 for the third item. And then these would also be balanced in the sense that they're not too low, but also not too high. Cool. Now, this was how we defined prices to be balanced. And we now generally say that a valuation function admits balanced prices if it admits these prices. So for every set of items U, there exists prices which fulfill these 2 inequalities for every set T. I now changed this definition here a bit. Before I had the set of S of items that I wanted to buy. Now I'm changing this to U take away T, which is just equivalent, but now this S has vanished and I'm only talking about the T here. Good. And now what one can show is that actually whenever a class of valuation functions admits such balanced prices, then whatever distributions you would take over any valuation functions in this class, then you would have static anonymous item prices such that this inequality holds, which is at the expected social welfare that you're obtaining is at least a half times the expected optimal social welfare. Now, how do you do that? Well, how would you set the prices? Well, not surprisingly, to set the item prices, we are now using the fact that these balanced prices exist, but these balanced prices only exist for a certain, let me go back to this slide, balanced prices only exist for a certain valuation function and for a certain set U, but now all we actually know is this probability distribution over valuation functions. So how is it that we're setting the prices? Well, let's first suppose that we know some valuation functions, which might not be the true valuation functions. Let's just see, we will now want to design prices for valuation functions v1 tilde through vn tilde. And these are our items. We have 10 items. What would we do? Well, we would consider the following sets. Let ui be the set of items that buyer I gets in the optimum on v tilde. So then, of course, each item is contained in at most one of these sets ui. Maybe we can even say it's contained in exactly one of these sets ui, because this optimum is partitioning the items among the buyers. And this is now what we're using to define the actual item prices. Because now we have that for vi tilde ui, there exists balanced prices according to our previous definition. So let now Pj superscript utility be the balanced price that we know exists for item J. This way we have now some balanced price defined for every item, but of course only defined for a fixed valuation profile. And now what you do is the following: the actual item price, you now define based on the balance price by taking the expectation over this over the valuation profile utility. So this is now where you use that you actually know the probability distribution over the valuations. So what you can now do is you just draw from this known distributions, you see what would happen if you were drawing from these distributions, what would be the Pj tilde that you would be ending up with. And then there's something confusing here, that we now scale this down by a factor of a half. So it's actually not that we're posting anything related to these balance prices, but we're scaling them down by a factor a half. Good. Now, why does this work? Why does this give us what we want? I will not go through the argument why we will be actually getting this half approximation of the optimal social welfare in the very general setting, but I'd like to now turn just to the setting where we know these valuation functions in advance. So in this full information setting, which I was also arguing about earlier, let's assume we know these valuation functions in advance. We know the entire valuation profile, which means nothing but that the probability distributions are just point distributions. They put all probability on just one valuation function. And now we can just define prices as before, but this expectation we had here for defining the price vanished. And also this V tilde just vanished, because V tilde and V, these would now just be the same. And how can we argue now that we're getting good welfare? Well, let now Ti be the set of items which actually should go to buyer I. Recall that Ui, this was the set of items that buyer I should be getting in the optimal solution, but Ti, now we say, okay, these are the items which are sold to some other buyer other than I. And so this is what we planned for buyer I, but somebody else bought this. What happens now? Well, let's see what happens to buyer I. What about buyer I's utility? Buyer I's utility is at least the following. It is at least, how much? What can buyer I do? Well, buyer I can, for example, buy UI take away Ti. Then they will have value of UI take away Ti, and they'll have to pay for everything in UI take away Ti. Maybe they're buying something else. Maybe they're buying a different set, but this is certainly a lower bound on the utility. And then everybody else is, of course, paying for these items in Ti. So this is what we're collecting as a revenue for items in Ti. Now, what happens now? Well, let's plug in the definition of this price here. If we plug in the definition of this price and use, and then we see, and then we use these balanced price conditions, then we see, okay, we get a lower bound for this utility here and an upper or also a lower bound for this part which was contributed by the revenue. This is now using these two inequalities of balanced prices, that this Pj bar was based on this Pj, which was not too high and not too low. And now the amazing thing happens, regardless of which set Ti, which we are having here, this actually cancels. All that is remaining here is always a half times Vi of Ui. And now we can just do this, take the sum over all buyers. We'll see, okay, we're actually summing up whatever is paid for each item only once. So this is exactly the kind of a sum of utilities plus revenue argument we've seen before. And with what we've also seen before is that it doesn't actually matter who buys the item or whether it is bought or not. Somehow this is the same kind of argument that I tried to convince you of before in the single item setting, where I wanted to set this price of a half times the maximum in that sequence, regardless of the one who's supposed to buy the item or somebody else bought the item. We're always covered. We are always happy with what we get. And the thing is now, this argument here, you can actually, well, I'm tempted to say you can write expectations around everything, which is not actually true. You have to be more careful here. You'll have to use some arguments using then that you're drawn these utility from the same distributions as the V, and you'll have to use some mirroring arguments. But nonetheless, this argument generally is robust enough so that you can write expectations around everything. And so this is how you then get the argument that also for any unknown, for any known probability distributions, you can get this half of the optimal social welfare. So this is what works out generally, and you can even go beyond this. Namely, what if your function now does not admit balanced prices in this very strong sense, which, by the way, if I'm not mistaken, is only true for XS functions? Well, then you can introduce some constant factors here. So you can introduce some alpha and some beta, and then this nicely goes through this entire argument. You can just generalize the argument that I was presenting to you, and then you'll get a 1/1 plus alpha beta fraction of the optimal social welfare. For XOS functions, you would get alpha and beta equal to 1. But for other classes of valuation functions, you can still get something. And oftentimes you will have actually small constants here, so that you can also get something reasonable for other valuation functions. Good. So what is it that we've seen so far? We've seen that combinatorial options, we've seen this general result, that if your valuation functions admit balanced prices, then you can actually get a good approximation to the optimal social welfare. Now, something that might make you nervous is that to define your price, you had to actually know the optimal social welfare optimizing allocation, which is NP hard to compute. But fortunately enough, you can even do without this. You can use the LP realization of the problem instead of the integral optimum, and you can still do the entire argument. And then you can actually also compute these prices in polynomial time. You can, in principle, also apply these techniques via balanced prices also for revenue maximization. Sahil was alluding to this in his first part. Then you need a lot more techniques to tackle this revenue question, but at the core, you will still use this these balanced prices to price your items. Now, what about beyond XOS functions? Well, as I was saying, you can, in principle, use these alpha beta to get something also for functions which are not XOS. But for example, for subadditive functions, this will give you only a log m approximation guarantee, because you can only get alpha beta balanced prices for alpha times beta being in the order of log m, and nothing better than this. But there you can actually relax the notion of balancedness, and then you can get down to a log m approximation, maybe even better. This is still an open question. Good. Now let's try to generalize this further, and let's try to move to other feasibility structures. And I'd like to talk about first Matroid profit inequalities, and let me try to give you a quick idea of what you can capture by Matroid profit inequalities, what you can capture by Matroid feasibility constraints. Well, I've tried to come up with a simple example. This is maybe not super convincing, but it is an example of a matroid. Suppose you are allocating now seats in a stadium, but unfortunately, due to social distancing rules, you're allowed to only sell 500 seats in the entire stadium. And then in each of these 10 blocks that you have here, you may only assign 100 seats each. So this first constraint would constrain you to 1,000 seats, but you also have this other constraint for the entire stadium, which would mean that you have only 500 seats there. This is something that you could capture by a laminar Matroid, for which you would then have a laminar set system, and then each of your sets you would have a cardinality constraint. And maybe what you would now want to do is you would want to apply what we were talking about earlier, but you would have on the items that you're allocating, you would want to have such a laminar Matroid constraint that you cannot allocate all items simultaneously, but only according to these constraints. The Matroid Prophet Inequality statement, which was introduced by Bobby Kleinberg and Matt Weinberg, actually installed 2012. I somehow didn't change this here. Sorry for that. This is actually, well, maybe a special case of what I was alluding to, but it's not quite, and not really different because the techniques generalize to this setting I was mentioning. So how would this work? This is very easy. You then have n bars of values v1 through vn, which are just now non-negative real numbers. And now the set of accepted bars has to be independent in a given matroid. For example, a laminar matroid, as I was alluding to. And now the buyers arrive online one after the other, reveal their VI, and then immediately and irrevocably, you have to accept or reject the current buyer. These VIs are again drawn independently from known probability distributions, and they arrive in a fixed order. So what we are now saying is that we can just accept or reject buyers. And there's only one way to serve a buyer, namely by accepting. And what Bobby Kleinberg and Matt Weinberg were showing was that there is an algorithm which guarantees that the expected social welfare that you're getting is at least a half times the expected optimal social welfare. So also this generalizes the standard Prophet inequality, where your matroid constraint would be just a one uniform matroid, namely that you're allowed to select only a single buyer. And now, regardless of what matroid constraint you have, this just nicely generalizes to arbitrary matroid settings. And how do they do this? Well, actually, what they're doing is still balance prices, namely, and this is how we phrase this in this Fox 17 paper in joint work with Paul Dütting, Michael Feldman, and Brandon Lucier. We showed that actually this, what Bobby and Matt are doing actually generalizes nicely to do the way we also saw this in the combinatorial auction setting. Mainly this works as follows. We can now generally say that for arbitrary feasibility structures, we can now define pricing rules to be alpha beta balanced with respect to evaluation profile and with respect to feasible outcomes. So X is just a feasible outcome, and X prime is another feasible outcome, which is still feasible after we've already allocated X. So before we had here some allocations of items, now we're just taking this to the next level and we're saying, okay, there are just certain outcomes. And we now say, okay, this pricing rule for a fixed valuation profile should be should now make sure that these prices are high enough, but they are not too high. And what do we now mean by high enough, but not too high? High enough means that now somebody else is buying some XI outcome, generally speaking, and this now reduces the social welfare that can still be obtained. V of opt of V, this is the optimal social welfare. V of opt of V given X, this is the optimal welfare that can still be obtained after having allocated X. And now, whatever people are paying when they are buying X, this should cover the loss in welfare this way. But on the other hand, when people are buying X prime, this should be no more than the value that is still remaining after X has been allocated. So recall that X prime is an allocation that is still feasible after X. So the general idea that you should keep in mind here is that this generalizes what we've seen for these balance prices for combinatorial auctions. Now, to make things even more complicated, you can make the prices here depend on what you've allocated so far. And this is actually necessary for the case of these Matroid profit inequalities. But before we get there, let's first see that what we had before for these combinatorial auctions also nicely generalizes here. Namely, if you have alpha beta balanced prices, then you will get a 1/1 plus alpha beta approximation to the optimal social welfare. And how would you do this? Well, in the case of a Matroid, what you would do is you would now say, okay, what's the price that I now assign to a buyer for being accepted? This depends on what I've accepted so far, which buyers I have accepted so far. And I'm now saying, okay, this is the loss in social welfare by not also accepting this further buyer. Recall that you're now defining these prices knowing some valuation profile, which might not be the true valuation profile, but you define this based on a certain valuation profile. And then you can say, okay, before my remaining opt was something like in the Matroid I had before, I say I contract the set A of buyers, which I definitely accepted. And then I compare this to what if I also contracted buyer I. So if I forced buyers A in the set A and also buyer I into my solution. And this looks a little different than what we've seen in the case of combinatorial auctions, but you can still verify that using now Matroid properties that this is 1,1 balanced. So also here you have the property that prices are high enough, but not too high. And you will also obtain the prices that you will eventually assign to the buyers the same way as before, namely you define prices like this for a fixed valuation profile utility, and then you're taking the expectation over this utility to define the actual price and scale this down by a factor of a half. And now what makes all of this pretty complicated is that the prices depend on the set of buyers that have been accepted so far, but as Feldman, Svensson, and Sandklusen showed in their paper on online contention resolution schemes, it turns out that these prices have to depend on what you accepted so far, and you cannot do without this. But the general spirit you should still keep here is that you're doing this full information argument, and in this case, it's actually more complicated because you'll have to use some Matroid theory. And then you can do the same, or kind of the same argument I was doing for the combinatorial auctions in a more general sense, and then write expectations around everything. Good. So coming now to the end of this part and also of the entire tutorial, I hope I've given you some idea of what these balanced prices look like, of how you work with these. And the general advantage of this is that you can actually take apart the entire argument. You'll have one part which will be about your particular feasibility constraints. There you will use only full information arguments. Like, I hope you recall this slide which I had where we just went through a couple of examples of why you had balanced prices for these particular valuation functions. This is the spirit that you'll have to follow then in the full information setting for your particular feasibility structure. And then this, if you are able to show these that you have such balanced prices, then more or less out of the box, this generalizes to the incomplete information setting where you actually know the probability distributions by, yes, I was saying taking more or less expectations around everything, which is not quite true, but maybe enough for today. This you can, in principle, also apply to the profit secretary setting. Unfortunately, we didn't have time to cover this profit secretary setting in which these buyers arrive in a random order. Unfortunately, it's more difficult there, but there's at least something that you can do there also with balanced prices. But there you won't get the optimal guarantees, or at least we don't know whether you will get the optimal guarantees for which settings. And in other settings where the order is just 1, 2, 3, and so on, there, well, sometimes you get optimal guarantees, like for example, for the single item setting, for XOS valuations, for Matroid profit inequalities. There you will get actually the optimal guarantees out of balanced prices. For other settings, we don't know, or for other settings, it's just not true. I mentioned the sub-additive combinatorial auctions, but I think also the matching settings Michal was talking about, I'm pretty sure that they're provably balanced prices will not give you the best guarantees. For other settings, it's still unknown, but usually via balanced prices, you can obtain a very simple baseline for every possible setting. And at least for these matching settings Michal was talking about, you will also be able to get at least some constants, although those won't be the best constant. So this is it from my side. Thank you very much for your time, and please do let me know if you have any questions.